In this video, we are going to talk about something called bond dipoles and then also molecular polarity. And it's kind of like what you're thinking it might be, whether or not stuff is polar, just like is the Earth polar? Does it have poles? That's what we're discussing today. Do molecules have polarity? Well, let's find out. So to begin with, polarity is going to describe something called dipole moments. A dipole moment is just simply an uneven distribution of electrons. So if you have something like what you see here of an oxygen connected to a hydrogen, notice how there's more little purple dots next to the O than there are next to the hydrogen. That's because oxygen is more electronegative than hydrogen, so it's going to pull more of that electron cloud closer to it. And so these little symbols up in the top left-hand corner, this one and this one, those are your derivative symbols, your partial derivatives. And so this one is negative and the other one is positive. And so what that means is hydrogen is partially positive and the oxygen is partially negative. And so is there an uneven distribution of electrons between this oxygen and this hydrogen? Absolutely. And so it is a polar bond. Okay, so polarity is describing whether or not there's an uneven distribution of electrons. Let's do lots of examples and explore this concept. So here's another kind of silly cartoon example way of thinking about it. Is electronegativity is going to tell you who's going to hog the electrons in a covalent bond, just as in this cartoon, the guy on the right is showing all of these electron blanket getting pulled over him. He is an electron hog. And so with electronegativity, it's who's going to hog it? Whoever's more electronegative is going to be more partially negative, while the other elements are going to left with more of a partial positive charge. All right, so this is just remember, go pull up your periodic table, go find your electronegativity values. You are going to need them in this lecture. Let's start out with a simple compound, carbon dioxide. It's not that it's necessarily simple, it's that it's easier to see where the electron density is going to lie. So if I were to ask you which element is more electronegative, carbon or oxygen, you would immediately say, oh, that's obvious, oxygen. Oxygen is definitely more electronegative, and you'd be right. And so you'd have a partial negative around the oxygen, a partial positive around the carbon, and another partial negative around the other oxygen. And so this compound is molecularly linear. And its electronic geometry is also linear. And so the big question here is this polar? Well, we have polar bonds and we have polar molecules, and there is a difference because this compound has polar bonds. Meaning, is there a polarity difference between this carbon and this oxygen? Absolutely. Same can be said for this one. There's a big difference between this carbon and this oxygen. Negative, positive, negative. But is the whole thing polar? What that means is if a molecule is polar, if you put an electric field, it'll flow more toward a positive side or a negative side, or it'll orient itself with the electric field, where the positive end of the molecule is oriented toward a negative end of the field and vice versa. And so in order to do this, we're going to think about how the bonds are arranged in space, and that's where the VSEPR configurations come into play. So before we do that, let's look at this symbol here. So instead of writing partial positives and partial negatives on everything, we simply draw these arrows, and these arrows represent dipoles. So this is used to explain whether or not you have polar bonds. And so you can put any of this symbol between two elements on a molecule to designate that bond as polar. Let's do an example. So with carbon dioxide, we know that this carbon is positive. So remember that partial positive symbol? It gets replaced by the positive end of the arrow. And then the oxygen is partially negative, and so it gets the arrowhead. And so the arrowhead is correlating with the negative side, and the arrow tail is indicated with the positive side. So carbon dioxide has two bond dipoles, one between each of the carbon and the oxygen. But is the whole molecule polar? Well, we know from our VSEPR that this molecule is linear. Since it's linear, this oxygen is essentially pulling this direction, and this oxygen is pulling this way. And if you have a tug of war, like what you see in this picture right here, who would win? Oxygen is electronegative, but there's no difference in electronegativity between the two oxygens. And so it's like having carbon stuck in the middle and having both of its arms ripped out by the two oxygens. Okay, they're both pulling equally and oppositely. So this would be the tug of war game that would last forever. Or another way of saying it, this molecule is not polar. It has polar bonds, but it is not polar itself. And so in thinking about each of these molecules, you have to ask yourself those two questions. Does it have a dipole, aka are the bonds polar, or is the whole molecule polar? And those are two different questions that you have to answer by looking at molecular geometries. Let's look at some more examples. Here we have carbon tetrachloride's Lewis structure drawn. So if this is the Lewis structure for carbon tetrachloride, does it have any bond dipoles? And how would we draw them? Try and draw that on your piece of paper now. Go ahead and stop the video. See what you got. You should have noticed that chlorine is way more electronegative than carbon. And so which part's more partially positive? The carbon is. So I always start with my positives by my more positive. And then you draw the arrowhead toward the negative. And it's the same for every single one of these bonds. They're all positively around the carbon and negative around the chlorine. And so each one of these bonds has a bond dipole. But is the whole thing polar? That's a great question. Remember before how we had to look at the molecular geometries. This molecule is tetrahedral, which means all of the chlorines are pulling away from the carbon. Are they pulling equally and oppositely? Absolutely. And so since that's the case, this is nonpolar. The molecule itself is nonpolar. Even though it does exhibit dipoles, it is nonpolar. Let's try another one. How about NH3? When we have its Lewis structure, where is the dipoles at for this one? All right, well, let's think about it. Hydrogen is going to be more positive than nitrogen, so all of my dipoles are drawn going in. And it kind of looks like maybe the hydrogens would cancel. Not really sure. What do you think? Everything's pointing in toward the end. And then this electron group, which way do you think that's kind of pulling? And so if you look at all of them, all of these arrows, you orient it like it would be in space. This molecule is trigonal pyramidal, which means it's not all on the same plane. These hydrogens are not equally and oppositely pulling. It's not like you have three all within a plane and they're all equally and oppositely pulling. That's not true. It's a pyramid where everything is pulling outward, or in this case, really pulling up toward this free electron pair, and then the electron pair is even pulling out. And so everything is pulling this way, and essentially we have one giant molecular dipole that is pulling straight through the electron pair of the nitrogen. And so is this compound polar? Absolutely, it is polar. But you have to look and think about what does the Lewis structure look like in the molecular geometry of the compound before answering that question, because this is not going to get you anywhere helpful. All right, let's do some more examples. So this table is not exactly like what you've seen before, but it's very similar. And so I have drawn Lewis structures here for you. I want you to draw the bond dipoles for each one of them. So go ahead and stop the video and do that now, and then we'll discuss them and then determine the molecular polarity for each of these molecules. Now that you've drawn bond dipoles, let's discuss the molecular polarity together. First, double check and see if you got the same thing I got. The positive end is the end of the arrowhead, and the arrowhead is the negative side. So for this molecule, it's linear. Since it's linear, it's all pulling along the same plane. But nitrogen's kind of pulling electrons this way, carbon's pulling electrons this way. So molecularly, the whole thing is getting pulled that way. So this compound is polar. What about this one? Where's it getting pulled? Is it getting pulled one way, or is stuff canceling out? Is it symmetric? That's another way of thinking about it. Absolutely. So this compound is also polar. Absolutely not symmetric. Absolutely polar. And so it's getting pulled all toward the hydrogen. And so it is trigonal. It's still a plane. So all of these three are in the plane. It's just all the electron densities getting pulled toward the carbon and then pulled toward the oxygen. What about here? We have a tetrahedral structure. It is very symmetric. All the chlorines are pulling equally and out oppositely. So is this polar? Nope, it's nonpolar. What about this one down here? This one's interesting. This is trigonal pyramidal. So think about the P at the top of the pyramid, and then you've got a triangular pyramid going below it. Okay, and then you have your electron pair up here. So the electron pair is pulling up, and your three chlorines are pulling down. Who's going to win? There's a lot of simulations that can help you answer that question. For now, we are just going to note that, yeah, it's definitely going to be polar because is chlorine going to pull equally and opposite as one electron pair? No. And so it's not. It's going to be polar. It's going to pull away from that phosphorus in one direction. What about here? The hydrogens are pushing up, if you will. The sulfur is pulling the electron density from the hydrogen, and then this lone electron pair is going to pull the electron density even further upward. And so this is definitely polar. All right, what about this one? Now, you may think, oh, doesn't the single and the double bond pull differently? Yes, but this is not linear. I did this example on purpose. This is bent. So the way I should have drawn it to help us see that it's going to be different is drawing it like this. Now, remember, this molecule is going to have resonance. And so it's not like you have a single bond and a double bond. You have like one and however many, a partial bond. And so the extra electron density is going to alternate between the two oxygens, making it so your bond length is the same for both the sulfur to oxygen and sulfur to the other oxygen. But they are pulling away, okay? This is a bent molecule, and the electrons are pulling up. So this is another case where you have a competition of vectors, if you will. So if you're mathematical, think about them as vectors. Who's going to win? Is it stronger one direction or the other? It's going to be polar is the important part, okay? It's definitely going to be polar. It's just a question of which one's pulling more strongly, an electron pair or oxygens. But it is going to be polar. All right, more practice. I want you to pause the video, determine the molecular geometry of each of the following Lewis structures, and then we're going to do one by one and determine their dipoles and their molecular polarity. So do that first. Determine their molecular geometry and then draw their dipoles. You should have gotten tetrahedral, trigonoplanar for B, linear for C, bent for D, trigonal pyramidal for E, bent for F, and bent for G. Now let's draw our dipoles. So for A, you should know that your dipole is going to be from carbon pointed out. So once again, this is carbon tetrachloride. It could have been carbon tetrafluoride or anything like that, but it is going to be non-polar. It's got that tetrahedral geometry. What about for this one? Everything is pulling outward. So you would think it would all cancel, but is it all pulling out equally? No, the oxygen is pulling more. So everything's going to be kind of with more electron density pulling toward the oxygen. And so this is polar with a molecular dipole headed toward the oxygen. Because if you compare oxygens to chlorines, oxygen is more electronegative than its counterpart of chlorine. So it is polar. What about this one? If you draw the bond dipoles, you're going to draw them like this, where carbon's positive and sulfur is more electronegative. Since it's linear, it's going to be symmetric and it's going to be nonpolar. What about these? I hope you can kind of tell that if you have lots of electron groups and it's not very symmetric, it's going to be polar, and that's true. What about this one? Same reasoning. It's polar. Okay, so look at the symmetry. Look at the electron pairs. If you have like a lone pair, it's probably gonna be polar, with the exception of when you have octahedral and you have the four elements around the central atom, and then you have a lone pair up here and a lone pair down here. Those can actually be nonpolar because they are all on the same plane. And then you have one electron pair above and one electron pair below. And of course, I'm talking about the octahedral square planar, but it depends also on what the atoms are, because if all four atoms are the same, then it's going to be nonpolar, but if it's different, then it's going to be planar. It's going to be but if the atoms are different, then it's going to be polar. And so look at these molecules and kind of think about, do they have a lone pair? Are they symmetric? Those types of questions. What about this one? We have two electrons. It looks nice and linear, right? But if we look back and we look at the geometry, it was bent. So a better way of drawing this is with chlorine, sulfur, chlorine, lots of electrons. Because now you can tell these electrons are pulling up, these chlorines are pulling down, but it's going to be a mismatch, and so it's going to be polar. Same thing here. except for the oxygen is pulling the electron density upward from the hydrogen, and these electron pairs are pulling upward as well. And so it is definitely polar. And if there's any molecule that is important to know whether or not it's polar, it's water. It's a very important molecule. So this is a good table to help you tell whether or not a molecule is going to be polar or not. So if it's linear like this, everything's pulling in opposite directions, the two atoms on each end are the same, it's going to be nonpolar. Same thing for these other situations where if it's either tetrahedral or trigonal planar, they're all pulling equally and oppositely, and so all three of these are examples where you have the most general case of an electron geometry and they're all symmetric and it's all nonpolar. Whereas as soon as you start having things like bent and some electron pairs, that's where you're going to start having these polarity issues. And so look at the electron structures and try and notice trends in both symmetry and bond dipoles to help you figure out whether or not a molecule is polar or nonpolar based on its electronic and molecular geometries.